This is a continuation of the modeling periodic data video. We got to the point where we were modeling this data set. These are the x's, these are the y's. And we had gotten to this model, y equals 2.1 cosine pi over 6x plus 1. And I wanted to show you some things about how the calculator does that and how to use that, and then also evaluating badness of fit. Okay. Now, I don't want to advertise this to the general YouTube public as the default method of finding the badness of fit, but it turned out to be what everybody in our class this year came up with. Look at the relative errors between our prediction and the data and take the average of that. And we're actually going to see something that's a little weird about that, something a little dubious about why you might not want to do that, but it's going to work somewhat here. And so that's what we're going to do. First of all, I just want to start out with something I did do in the other video, but we'll do it quick. If you go to Stat Calc, there's a lot of funky stuff in there, and way down at the bottom almost is Sine Reg. And I showed you how if you put in L1, which is where our list of x values was, and L2, that gives you a function. And then the question is, well, what do I do with that? What if I wanted to graph it or something? What you do is you put in a third argument, which tells the function what variable I want to store that in. And I'm going to go to vars, then yvars, then function, and put in y2. The reason for that is y1 is already set up with this function. Okay. So, chugs for a minute, comes out with something that we talked about in the other video is pretty close to equivalent to ours, but we'll see it's an interesting difference. And then we go to back to y equals, and it's loaded that in automatically. Okay. So now we'll go to the graph. There's our data. This is our guess, and it starts out good, but then starts getting off a bit. And then here's the new one. You can hardly see the difference. It's halfway through, and then it starts diverging. And it does really seem to nail those three last data points a lot better. Okay. So let's make that quantitative. And again, this is with a particular version of badness of fit. And I want to show how we could do that somewhat efficiently with the calculator. Okay. So let's go out of this mode. And I want to use some list stuff here. So what we're going to do is let's look at our model, the y1 function. So vars, yvars, function, enter. And I'm going to feed into that y1 function the appropriate x values, which was L1. That was a list of x values. Okay, that's just going to give us basically the heights at the correct of our model at the data points. And I want to compare those to the data points. Those y values were in L2. That gives us a list. That little arrow here says if you could push the right arrow, you can go over. And those are the list of the absolute differences, the absolute errors. They start out with 0, notice, because we made sure that first one was right on, and then they become more or less accurate as you go on. Now, one thing I want to do is not pay attention to the signs here. I want to take the absolute value of that. So I'm going to modify that a little bit. Math num abs. Here's the new operating system, how that puts that with absolute value bars. And let's just do that again. Vars, yvars, function y1 of L1, which is shift 1, minus L2. Okay, that's the absolute values. Now, the proposal was not to add up these or average these guys, which would actually be a very, very reasonable method of badness of fit. Another version is to square these guys and then add them up. That's probably the most popular version. But the version we came up with was to take these guys and actually turn them into relative error, which means take the difference between your prediction and the actual and divide it by how big the actual is. So as a proportion of L2, the y values, what are these guys? Still starts with 0. Then it's about 2.4% for our error here for this example. And then I want you to notice something rather striking. 1.25, that's huge. That is 125% error. And we'll go back in a second to see what's going on with that. Then, 0, which is good. Then minus, that's because that's that minimum. We made sure it went through the maximum and the minimum. Minus 83% error, that's not good. Okay, now down to 20%, 28% error, then 7%, then 18%. Not so great when you express it in terms of percentage error. The reason for that is, like these points in here, especially this one, this had the 125% error. That's because it's so close to the axis already, even a small difference. This doesn't look like it's very far off. If we insist on using relative error, that's going to make that look like it's a huge contribution. That's why most people don't use relative error in this kind of example or in this kind of method, but it's interesting that that came up in this example. Okay, so let me go back. So there's all the relative errors, and then we just need to average them. That was the proposal. Okay, and so I'm just going to go to stat, calc. Let's see, actually no. Let's see, where are we? It's actually a list. Sorry. List, math, mean. There we go. And just ants, because it's sitting right there. That was the previous answer. I'm just going to take the mean of the previous answer. So the average is 12% error. Okay, so let me write that down here. Average for our fit, about 12.1% error. Error. Okay. What about for the other fit? Well, all we have to do is do exactly the same thing, except put in a y2, and just almost the same thing. So let's just go back. I think I'll be able to do it with the second entry here. Yeah. Okay, so we're going to put in vars y-vars function y2. So that evaluates the y2 function, the sign reg from the calculator, at the appropriate x values, compares to the y values that really were the data, takes the absolute value so you don't let minus signs and plus signs cancel out, divide by the size of the data, and that gives us a list, probably a lot smaller numbers. And let's just go ahead and do second list, math, mean of ants, and a lot better. So again, partly this is because we're using this idea of relative error. Average for calc's fit. I don't want to give the impression that our fit was so terrible, but certainly by this measure, this is 1.4% error. And both because it really was genuinely a better fit, it looked clearly better, and because right in here you get this phenomenon that any error we do is going to be magnified, these two data points especially. That made it look like our fit was pretty terrible, and the calculator's fit was better. Okay, so that's how that proposal works out in practice, and we'll try and do that in class as well.